So let's switch to slides and adjust. From here we will go. Hi everyone, this is going to be the video about the curvature formula. Was just introduced in our calculus 3 course, but along the way, after we define the curvature formula, and I will introduce or mention briefly about how this idea of the geometric part went into Einstein's theory of general relativity. So first, what's written here is RT is a vector function in three-dimensional space, or you can look at it as a position function after t seconds if for more physical situation, and R prime t is a tangent vector, first derivative, and R double prime second derivative, of course. And in physical situation, these will be velocity vectors and acceleration vectors. What you see here as s equals st is the arc length function. So these are scalar functions. So from the position u equals 0, as an example, to u equals t, where t is varying, the arc length of the space curve can be computed by computing this definite integral. So integrand inside here is the absolute value of the velocity vectors. From there we have this interesting fact about this st is a scalar function. So we can think about the derivative by fundamental theorem of calculus. The derivative is just this integrand with t in it. So it looks like this, exactly the velocity. And that kind of makes sense, that because st is arc length function, so that measures how much it moved, the distance it actually moved, and we're taking the ratio over with the increment at the time. So that must be measuring the instantaneous velocity of that, and the right hand side is the magnitude of instantaneous speed. That's what I meant on the left hand side, and the right hand side is the magnitude of the velocity vector. So it kind of makes sense. But if you think about it, on the other hand, we formally define this velocity vector right there, or tangent vector, and this is a slightly different idea, although it kind of inside the idea it's kind of using the same thing, but it's a neat mathematical way of describing that it's if that particle has a built-in speedometer, and what it reads inside is really the magnitude of the tangent vector we have defined over there. So this part is, let me move this slightly, can't quite fit everything in it, but here's an RT is smooth, and it means this velocity vector is never zero. This, for technical reason, we put this one in so that we can define something called unit tangent vector. But if you see this part here, if r prime t is never zero, that kind of guarantees that it keeps going in the same direction. The orientation of this space curve never changes. Therefore, s equals st is a constant increasing, but the t value that corresponds to this given arc length is going to be unique, so that when you reverse this process, s as a function of t, which is what we have described here as s as a function of t, can be reversed because it went through the one position of that path and then it never comes back, because this r prime of t is never zero. In physical situation, it kind of makes sense to change the direction. You have to stop and change the direction. So by putting this condition, we know this keeps going in one direction of the space curve. But right now we're just using this for this definition of the unit tangent vector, which is going to be the important tool to define the geometry of the space curve. So tt is the unit tangent vector. So this is really that tangent vector or velocity vector, but is rescaled so that it only has length 1. So when you scale it, we have this denominator, which is the absolute value of the velocity vector, and we don't want that to be 0. So here's the situation in the picture. This is where the origin is, and dot dot dot, and that's the position. So the vector is the position vector there. And this is a velocity vector r prime t, and we rescaled it to this tt. And this space curve is kind of turning to the right of that tangent vector. It's kind of suggesting something is pulling in that direction. That's a physical interpretation in mathematics, and this velocity vector is about to turn to the right as we point to this and that part of the curve. So the change, the measure of the instantaneous change of this velocity vector is kind of that. But this picture sub doesn't quite show how this magnitude of the velocity vector in the next moment is, so it's guessing by just looking at this picture how this double prime t, it's not possible actually. But if we ignore this as a motion of something, but you just look at this path as a geometric object and ignore how fast it's moving, so rescale to tt, and then we have a good prediction of this shape of gamma prime t if we just focus on this tt. And that's the idea. To look at the geometry, we got to play with this unit tangent vector. Alright, this is now the definition of the curvature. So this definition of the curvature uses this arc length s that I don't think I gave enough explanation on this part, but s here stands for arc length, and we thought about this relationship between t and s. T is the parameter, or if you like, it's going to be the time, and the arc length. The relationship between t and s is 1 to 1. It visits the one position only one time, one value of t, because it was smooth, because the derivative of r is never 0. It passes through and never comes back to that position. So the key thing is that's looking at this change of the unit tangent vector in terms of the arc length. So let me show you the picture. So what this really measures here is that this is kind of overall behavior of the unit tangent vector at s equals 0. That's the beginning point. Here at s equals 1 is the position where the arc length from that position to that is exactly 1. So you can see how much this unit tangent vector in here is turned around. And over here in s equals 2, if you compare it with s equals 0, it turned out a lot. So to comparing all this in derivative form, what we actually do is that we parallel transport these three vectors into position so that all the point of applications are the same, and this tangent vector we're looking at is just unit length, so it's kind of being turned around as s increases. The key thing here is that we're looking at these changes of the unit tangent vector in terms of the arc length, and when we do that, we capture the geometry of this path, not really considering how fast it's going through. So the curvature is about the geometry of this curve, so this is actually a pretty cool definition. So here's an example. RT here is known as a standard helix, and x and y projection, you get this cosine t and sine t, and that's a standard circle. As you look at the z component, t increases, so it's like in xy plane, if it is projected or sheds a light toward to the xy plane, it just keeps circling around. But if you look at the actual space curve, and t keeps increasing, so it's kind of coming up, around, going around. So it looks like this rough shape. And we went through all the definitions. So you compute this arc length and reverse an s and t relation right there, and then you get the formula of this unit tangent vector in terms of t, and then plug in this ts in there. And now everything is in terms of arc length. Now you differentiate with respect to arc length, and so on. It turns out everywhere, it doesn't matter where you are in the helix, the curvature turns out exactly 1/2 all the time. So let me explain the meaning of, in general, it's not true if you look at some arbitrary vector function of one scale input, the parameter t, this curvature changes. But in this case, it was a constant everywhere. So let me give you a little sense about what this curvature 1/2 means. And this is a circle. So when you look at the circle, it's another example that everywhere the curvature is the same. We understand a little bit better about this circle than this helix. So it's all around. If you sample this point or sample that point or sample that point, it's kind of exact, a congruent copy. If you do some sort of rigid motion in this plane, you will be able to change this piece exactly like that. So since curvature, definition of the curvature really captures the geometry, that it's reasonable that the curvature around the circle is exactly constant, and that we go through this computation again. We're using this definition, which is feasible because this computing TS is not so bad. Then it turns out it's constant. It is 1 over a, and it has been standard thing that if you're looking at some arbitrary vector function at one position, you've got some curvature there, not necessarily constant, then how do we compare that? How do we get a sense about how much is curved? Then you look at this circle with a radius. For example, if it is 1/2, then we're going to look at the circle of radius 2, such that its curvature there everywhere is going to be 1/2 because of this formula right there. Then we have a little better sense, and it's this piece there curved just like this piece right there. So you've got to have a 1 unit kind of drawn right here, and then you can compare, okay, 1 unit, how much is being turned around, and that's the key thing here. So let me see. So that was my little introduction to the definition of the curvature, kappa s. So this is reads kappa, not k, Greek letter. Now let me introduce the formula. If you think about the definition of the kappa, let me show you briefly. So here, this part is the definition, where we use this TS, and I was kept saying that this computing TS is often very difficult, and actually most example is kind of impossible. So let's go back to the formula. So here's a formula again, and what's good about this formula is this formula doesn't require to calculate that TS, the relationship between the parameter t and the arc length. It only involves this r prime t, which is straightforward to calculate if you have a formula for that r of t. So here it is. That's the one great thing about this formula. So another interesting thing is this geometry of physics. So here's an example, and I want you to think about this path. Suppose there's this path, and a vehicle is about to go through this path, and we have information about how this one is, positioned. So suppose we have information that the curvature at that point is kappa. I just realized that I made this slide a little bit backwards, so I want you to ignore these condition on this part for a moment, and I just want you to focus on this formula here. So I copied this kappa formula, it's written here, down here, and there it is, this formula. So we're in the numerator, we're looking at the absolute value of cross product, the magnitude of the cross product. So we know this formula is product of those magnitude times the value of the sine, where this theta is this angle between the velocity vector and acceleration vectors. And so we got everything. So if you cancel those common factor, we got the following. So kappa equals magnitude of acceleration and sine theta and so on. So we're thinking about the situation here that we're about to making this turn, and this vehicle has limitations. So the magnitude of acceleration this vehicle can generate is, let's say it's A, capital A, and that's limitation. And the question is that, actually I realized that the order of this slide is correct, and I just forgot about what to mention here. So that was a situation, there was a path there, and we know how it's curved, so we got the curvature, and the situation of the vehicle has the limited amount of acceleration it can generate. And looking at this formula of the kappa that is introduced in here, and we have the following, that kappa is related, have this inequality, and what this implies is interesting, is the following, that if you solve this inequality altogether for absolute value gamma prime, and we have this inequality, what this means is that if the acceleration is limited like this, and if you're going through a path with this curvature kappa, then the maximum speed it can generate at that moment is governed by this inequality. So this is very interesting. It seems like everything about some nice physics problem, and the answer to this type of question comes from completely in geometric flavors like that. So I titled this example an application as a geometry of physics. So that's the second application, or the things that I like to mention about this formula. It's a cool thing about this formula, the application to the geometry of the physics. It allows you to physics problem more mathematically using this great notion of the curvature in geometry. Before we actually go into the details of this formula, let me mention this historically important thing about this curvature in humanity, actually. So we just looked at the definition of the curvature of space curves. Later, Gauss defined the curvature of surfaces like this. I want to look at this as a portion of an ellipsoid, a little piece of ellipsoid, and we can think about a little one point on that ellipsoid. And we can think about, okay, it's not like flat, it's kind of curved around. So Gauss nicely defined kind of measure on how much this one's curved, and that his success was lying in the fact that his definition can be extended to the abstract level. So we're not only looking at the surface in three-dimensional space, but surfaces in high-dimensional space, or surfaces in a very abstract situation. This curvature is well defined and still intrinsic, turns out to be intrinsic property of the surface. So that was his accomplishment, and Riemann, as a student of Gauss back then, nicely generalized this idea not only to the surface, which we call a two-dimensional object, but Riemann defined this one for the higher dimensional objects, and its definition is quite complicated, but that was a great success. This curvature idea was extended to a higher dimensional object and more abstract space. Later, Einstein, once after he got the recognition out of his success in the special relativity, and Einstein was driven to do something about the gravity, and then his idea was that using this curvature, and was actually this idea was tipped by the mathematician Minkowski, but it's Einstein's accomplishment to kind of bring that into a complicated physics situation. So here's why it's connected to kind of brief explanation, is that if there is a gravity, whatever the source of the force is, and then if there's an object, there's no other forces exerted, only the gravity is causing these things and moving not in a straight path and in a different path like this. And Newton was thinking about acceleration vector, but Einstein's idea is that, okay, look at this things that, the path in here is curved around, and why don't we think about the curvature of these things? Not only in this three-dimensional space, but in space-time, and that's quite tricky. When you enter the space-time, it gets really trickier because time becomes a vital part of this dynamic in this space and time. In this abstract space, and he looked at this freely falling object and how is this curved around in the space-time. Maybe you should measure these curves of thing and directly relate it to the gravity, and that was his idea, but rather than looking at these acceleration forces like Newton did. So I'm showing this picture again, so it's like suppose this is not the path, but it's actually freely falling object, and it caused the bend because there's something is pulling toward that direction. And then if you look at this formula, this curvature itself has kind of all the flavors in it that Newton was thinking about, and so Einstein was thinking about, why don't we just focus on this type of information. So we're back to slide again. So that was his idea, that in space-time it's not curve or space two-dimensional, it's a four-dimensional complicated space, and he wanted to come up with a nice curvature idea. So this is known as famous Einstein's field equation. So he just think about the geometry of the physics really seriously, and then came up with this Einstein curvature, and which is directly proportional to the source of the gravity, and inspired by the electromagnetism. That source of the gravity is not just the mass of the thing, but whatever has inside is going on, that he called the stress and defined as a stress energy tensor. So these direct proportionality of this curvature and stress energy tensor as a source of gravity is called Einstein's field equation. So you can feel it in a curvature important notion in the geometry became a big deal in the physics as well. And so this is the statement that we should call this it's a big theorem and in geometry and physics. Now let's do some mathematics, and this is actually the formula again. Then we'll look at details of the statement, and it might look a little bit technical, but to make a great connection from physics and then its geometry and its nature of how things work, and you have to look into this mathematics. All right. Okay. So the first thing we'd like to recall is this formula of a triple product, a cross product. So I usually use this picture. I forgot to put it in here, but let me just say that this is a cross product of two vector A and this B cross C. Therefore, this vector is perpendicular to the B cross C by definition of a cross product. Now, any vector that is perpendicular to B cross C is generated or spanned by this B cross C. You have to draw this little picture about this B cross C, and then you will easily understand, okay, the right-hand side is really linear span of B and C, so it makes sense. I made another video about this property, and in there I explained this why the A dot C and A dot B kicks in there. But it basically is coming from how the scalar projection or vector projection onto other vectors works, and it's really coming out of there. So that was one, the fact that I'd like to use in there. So another thing is has more physical meaning to it, and this is really geometric flavor in it, linear algebra, and then really geometry of space. And this one is more calculus, and also it's important meaning. So WT is just an arbitrary vector field and vector function in mathematics, but you can look at it as a position vector or a velocity vector. So this one is measuring the rate of change of the magnitude of the vector, magnitude length of a position or vector, or the speed or magnitude of acceleration, however you interpret it. So right inside this is the rule. And this is something that not many people are familiar with, but the proof comes from this fact that the square of the magnitude of a vector is the dot product. And so out of there is a proof is straightforward, but this is some fundamental fact that in physics that we need to get used to. Okay, the rate of change of the magnitude of this vector, velocity vector, acceleration vector, works like this. Seems like important statement. And another thing is something we mentioned earlier is the arc length, and by fundamental theorem of algebra, we look at the definition of this arc length, and this one pops out. So these are the three things that we're going to be using, and everything is very, very important if you think about it. It's a geometry, some facts about these important geometry of vectors, and here's some calculus, 2 facts about rate of change. Now, proof starts like this. So this is the definition: rate of change of a unitangent vector with respect to arc length, where this t is replaced in terms of s. So next part here, we're using the chain rule. Since t is first calculated in terms of t, so if you can differentiate with respect to t, that will be convenient. So these dt cancel, and it works out like this. And the second term, which is a scalar right here, multiplied to this vector, so this is not a dot product. And in the second factor here, we're looking at t as a function of s, and that's something to note. And I'm ready to move on to the next part, but it's always tempting to stop, and whenever this happens, and I thank Leibniz about his wonderful notation, where you don't think about what's really happening in mathematics behind the scene, but this is called the chain rule, and it is just fantastic in how it works. So, Another thing is flipping this as if we can consider this dd as a quantity like the delta t and delta s is a correct thing to mention, and here it works still nicely. So if you flip it, it goes to the denominator of the rest of the part. Then you have to think about the role of s and t again. So now we're looking at s in terms of t. Then that's what happened from this part to that part right there. Actually, this part to that part, and we know the rate of change of the arc length right there is the magnitude of the velocity, their speed. So we got that part out, so we got rid of that part. So this is nicer, the unit tangent vector with respect to the derivative with respect to t. So let me go back to the previous slides, right there. So this was what we were, and then what we're about to do is we separate this part right there and then work on that part. So move on to next slides. So we look at the definition of this tt, which is this unit tangent vector. So the tangent vector divided by its own length, the unit tangent vector, and we're about to differentiate it. So if you look at the component of this vector, it's really like a quotient of two scalars. So you can actually use a quotient formula. So it's a quotient formula of a derivative. So the denominator is squared, and the numerator r prime is differentiated, but vector comes in the second position, so I wrote it here, and the denominator right there is copied over there, and minus, and this time the denominator is differentiated and numerator nothing happens. That's how the quotient rule works. So let's think about this derivative of the denominator, so I put it that way rather than just writing down the answer. So I forgot to pause it. So here, there was its formula. I copied it down here. So the derivative, instantaneous rate of change of the magnitude of the vector, how it's going to be, and that was some fact that coming out of the product about dot products. Alright, so I hope you remember that part. So we're going to replace that, this portion, this one. So here the w is this r prime. So r prime goes there, and r prime goes there, and this w prime will be r double prime. So it looks like this. So that portion right there is replaced by this formula right there. Alright, so this whole thing is a scalar and multiplied to this vector. That's why this big bracket and to distinguish which one's vector and which one's scalar. So we're here. The next thing we're going to do is that we're going to factor out this denominator, absolute value of gamma prime, outside, and this is what you get. So you get another copy, so that becomes third power, and there was a 1 power, but we factor out from the denominator, so we have to bump up, so that becomes second power. That denominator disappeared. It looks like this. So I think I put it into a nicer form than next. There it is. So this square of absolute value vector is equal to dot product, and this one here, it's a scalar right there, so I put in the parenthesis. So I want you to pause this video a little bit and think about this part right here, and then I want you to discover yourself, and then is that something that we reviewed minutes ago? And I hope you discovered what I discovered here. So let me go to the next slide. There it is. The triple cross product, it kind of fits into that. So let's see if it really fits in here. That this one, if that one fit into this on the right hand side, this B should be R double prime, and this C should be R prime. So where does B appear? And right here, that's R double prime. And that's the only spot that B appears again. So let's look at A. A must be this R prime. That's where the same place is. And then other place in here is this R prime. And C is this position. The R prime must be that C. Then another place the C appears right there, and then it seems like this one. So everything matches. So from there, we got this wonderful formula. Let me adjust this so that it fits in. So we got this third power down there, and all this linear combination of R double prime and R prime, and became this packed information. It's a triple cross product. So here we go. Again, this dt, ds right there, was originally the by chain rule. There is this derivative unit tangent vector with respect to t plus this one, we figured out that part is r prime down there. So if you think about what that were before, that it has a third power, now it has a fourth power. So that's really the rate of change as a vector of the unit tangent vector with respect to arc length. And let me summarize it here, and that's what this is. Well, let's think about the kappa. What kappa was really the absolute value of what I had just shown. So I put the absolute value around it here. So that's kappa s. Looks like this. Good. Now, absolute value of a cross product, that's what we're looking at. So this cross product 2 vector VNW, I want to look at it that way. So let's see. Hey, we do remember that cross product, the absolute value of cross product is magnitude times the sine theta, where theta is angle between these two factors of the cross product. One is r prime, the other is this cross product itself. So what is the relationship between r prime and r prime there? Is that this vector is perpendicular to r double prime and r prime. It happened that r prime is right next to it, so theta must be 90 degrees. So sine theta is going to be 1 because theta is 90 degrees. So that simplifies this whole thing down to this following form, where there's 1 copy and 4 copies down there, so it simplifies to that. So we arrived to this Kappa formula by looking at this 3 important thing about cross product, some geometric fact, and 2 calculus result about the rate of change of the magnitude of a vector function. And the last one was about the derivative of arc length scalar function. So that arrives to this formula, and plus this has this nice interpretation and application to the physics problem, and it involves velocity and acceleration and how they're tied together into something with geometric information. This is kappa, the curvature of the path. So I'm showing this part of the slide again because this is where that all things happen together, where the geometry and the physics, and then you can, if you want to feel this one mathematically, and this is the spot where you have to feel then how these 3 properties that we reviewed kicks in together with the algebra and calculus. So here it is. Feel it.